So after talking about pathwise connectedness, we're going to be discussing real topological connectedness. Why do I call this real? Well, forget about this result for the time being. Real connectedness is kind of stands to pathwise connectedness as, I don't know, real food stands to baby food, right? That's the baby concept, the concept we can visualize. This is more abstract, but somehow it's also more interesting. It has more structure to it. So, okay, here I define now what a connected topological space is. I define what a disconnected topological space is. So the opposite of connectedness is when you have a subset of X that's neither empty nor everything, which is both open and closed according to the topology. So that's the same as saying that L is not everything. L is not empty. R, which is a complement of L, is not empty. L is open, and L complement, which is R, is open. Right. So here's an example of a disconnected space, and you should think of it as a region in the plane. But look, I'm only defining connectedness of a topological space. When I talk about a subset of something larger, you need to consider the relative topology. So actually, let me start with to tell you, it makes more sense to give an example of something connectedness. So think that X is a box in the plane like this. And suppose I try to divide it into two parts, L and R. What would it mean to say that both L and R are open and closed? It would mean that given any point here, it has a protective bubble entirely inside R. Any point here, it has a protective bubble entirely inside L in this case, and entirely inside R in this other case. So if I could split X into L and R, which are both open, that would mean that any point is safely inside one of these two sets. And intuitively, that means that there could not be a boundary between them. Because remember, the boundary consists precisely of those points such that any open set around them intersects both L and L complement, which is R. So this brings us to this theorem. One of the things we're going to see is that a topological space is connected if and only if, whenever you find a region inside it, this region that's not empty nor everything, this region has a non-trivial boundary. So that's the same thing as saying you cannot split X into two non-trivial parts without having a boundary between them. But there are other equivalent statements. So 3 is sort of silly, but it's useful sometimes. Is that it's saying that the space is connected if and only if any continuous function from X to the discrete set 0, 1. Well, if it's continuous, it has to be constant. So that's the same thing as saying there's no way to paint, so to speak, X with two colors in a way that doesn't produce a discontinuity somewhere. It doesn't produce a sudden jump from 0 to 1. And the fourth is even more interesting, which is topological space is connected if and only if any continuous function from X to the real line has an image, which is an interval of the real line. So the intermediate value theorem, which I mentioned in the previous video, is a theorem that basically says that if you have a continuous function defined over an interval of the real line, right, to a domain that's an interval over the real line, its image is also an interval. And that's actually an if and only if, because if you have a set that's not an interval, say the real line missing 0, then the identity function of the set has an image which is not an interval, right? So a subset of the real line is an interval if and only if, when mapped by a continuous function, what you see on the other side is always an interval. Now, connected spaces are precisely the topological spaces for which you have a similar property. The space is connected if and only if its image under any continuous function to the real line is an interval. And that's kind of cool. That's one of the bits of structure that are going to be seen. Okay, so let's start by proving this result. Okay, how do we show that 1 implies 2? As I said, 1 and 2 should be closely related because of this idea of having two sets with a boundary. So I'm actually going to prove that not 2 implies not 1. So I'm going to assume there's a set of an empty boundary, right? So with an empty boundary. And we know that the boundary by definition is just the closure of S intersect with the closure of S complement. So I'm arguing that that's non-empty. And here's the thing. Those are the two, I'm going to define L and R as these two guys. So I'm going to show that if the boundary of S is non-empty, then X is disconnected. So I have to check that these two guys, well, I want to prove that L is both open and closed, and it's non-empty nor everything. So the way I'm going to prove that is to argue that R is the complement of L, that R is non-empty, L is non-empty, and the two sets are closed, right? So if the complement of L is closed, then L is open. We know right away that L is closed because it's a closure, and closure is always closed. And yeah, so in order to prove that L is not everything, what I need to do is to prove that R is non-empty. So how do I prove these things? So first of all, let me argue that neither set is empty because L contains S, right? The closure contains S itself, and R contains S complement by assumption S is non-empty and S complement is non-empty, right? Meaning S is not everything. So we know that they're non-empty. We know they're disjoint because of how we define them. We're assuming the boundary is empty. We know they're both closed. So now I'm going to try to argue that their union is everything, which is the same thing as saying that R is L complement. And why is that? Well, okay. First of all, I know that R is contained in L complement. And why is that? Because, well, okay, L does not intersect R, right? So all elements of R belong to the complement of L. And similarly, I know that L is contained in R complement, so that's the same reasoning. Now let's try to do something deeper, which is this. So I'm going to try to argue, I'm going to try to say something about the complement of L starting from this thing here. Also, I know that L complement, so we saw that in class, maybe in an exercise, that the complement of a closure is the interior of a complement, right? So L closure is the interior of S. What's the interior? Is the interior of S complement. What's the interior? So the closure is the intersection of all closed sets containing S. The interior of S complement is the union of open sets contained in the complement. And that's how you prove, right? That the complement of the closure is the interior of the complement. Okay, so L complement is the interior of S complement, which is contained in S complement, which is contained in R, because R is the closure of this guy. So now I've reversed inclusion, right? So I had that R is contained in L complement is contained in R, and therefore R is L complement. Okay, what have I shown? I took two closed sets, S bar, S complement bar. I argued that they're non-empty because I'm assuming that S is non-empty and the complement of S is non-empty. So these two sets are disjoint because the intersection is null and non-empty. Moreover, these sets have to cover everything, meaning that R is the complement of L. How did I show that? Well, first of all, if S bar and S bar complement are intersect, then clearly R is contained in the complement of L. On the other hand, I also argue that L complement, I know how to write it down, is the interior of S complement, and the interior of S complement is contained in S complement, which is contained in R. So I have that R equals L complement. Okay, so I'm done, and I'll explain why. So I found two subsets of X which are both closed. They're also both non-empty. And one is the complement of the other. Therefore, look at L itself. L is closed, and its complement is closed. So therefore, L is open and closed. L is non-empty, but it's also not everything because its complement is non-empty. Therefore, L is precisely a set of this form, a set that's neither everything nor nothing, which is both open and closed as a subset of X. That means that by assuming that some non-trivial set has an empty boundary, I can prove that X is disconnected. Therefore, I've proven that when 2 does not hold, 1 must not hold. And conversely, if 1 holds, 2 holds. And that's the implication I wanted. Okay, so that's the first implication of the proof. How do we prove the second implication? Which is 2 implies 3. And, sorry. Okay, so how are we going to prove that? Okay, let me, let's prove again in contrapositive form that if there is a function that's continuous and non-constant from x to 0, 1, then there's a subset of non-trivial boundary. Okay, so assume that x 0, 1 is continuous but not constant. What does it mean to say it's not constant? Well, it means that precisely this, that S, which is eta minus 1 of 0, is non-empty. And S complement, which is eta minus 1 of 1, is non-empty. Right? These I'm defining S and S complement. Why are S and S complement this? Well, every point of X is either mapped to 0 or to 1. And saying that the function is non-constant is to say that there are points that are mapped to 0, there are points that are mapped to 1. Therefore, S and S complement are non-constant. There's something more to this, which is S is closed. Why? Because eta is continuous and this is a closed subset of 0, 1 discrete. S complement is also closed. So if you like, we are proving, if you take these to be L and R, we're proving that X is disconnected. But if you want to stick with 2, then we just argue that, okay, the boundary of S is an intersection of closures. We know that when a set is closed, its closure equals itself. And that is empty, right? Because we have S and S complement. Therefore, if there is a continuous non-constant function from X to a discrete 0, 1, there is a subset of X whose which is non-trivial, right? It's neither empty nor everything, whose boundary nevertheless is empty. And therefore, not 3 implies not 2, so 2 implies 3. Okay, so that's easy. And now I'm going to argue that 3 implies 4, and that's also not too hard. In some sense, actually, what we're going to see is that 3 and 4 are equivalent, and that's more or less easy. And, okay, so I'm gonna okay. Suppose 3 holds, right? Now I'm gonna prove that for any f you have an interval. So I'm gonna assume that again I'm gonna prove everything in contrapositive form. I'm gonna say suppose that there exists an f x of r such that f of x not interval. So what does that mean? As we saw last class, it means that there are points in the real line ordered like this, such that t and t prime belong to f of x, and t double prime, sorry, and t prime doesn't belong to f of x. Now, how I'm going to define? I'm gonna define a new function, which is well defined over the real line minus point t prime. It goes from r minus t prime to 0, 1. And this function takes a value r and maps it to 0 if r is less than t prime, and 1 if r is larger than t prime. So I'm defining this function for all numbers that are not t prime and saying it's 0 to the left of t prime and 1 to the right. And this function is continuous. Well, it might not look like the part, right? Because you have t prime here, and this function is 0 up to here, and 1 from here on. But it's continuous because this point is not in the domain, right? So if I have a convergent sequence in r minus t prime, it has to have a limit that's different from t prime. So the limits either here or here. In both cases, you can check that you have continuity. Okay, so I have this function, and now I'm going to define eta, which is simply the composition of psi with f. And I claim that, sorry, this goes from x to 0, 1. This has to be continuous because it's a composition of continuous things, and it's well defined, right? So notice that the image of f, by assumption, does not contain the point t prime. Therefore, the image of f is contained in the real line minus t prime. The composition is well defined, and it's a composition of continuous things, therefore it's continuous. So I have a continuous function from x to 0, 1 discrete, but it's not constant, right? Because remember t and t double prime. So t is here, and t is the image of somebody in x by assumption, right? Here I have t double prime. It's also the image of somebody. So when I look at what happens with x and x double prime under eta, what I have is that, okay, x is mapped to t, which is mapped to 0. So eta of x is equal to 0. Eta of x prime is equal to 1 because x double prime is mapped to 1 because f of x double prime is t double prime, which is mapped by psi to 1. So this is the graph of psi. Okay, so when I have a function whose image is not an interval, I can compose it with this psi and get an eta from x to 0, 1 discrete, which is non-constant, but it is continuous. So that proves that when 4 does not hold, 3 cannot hold, therefore 3 implies 4. And actually the other direction is really easy. So assume that this guy holds, right? If for any function, the image is an interval. Now you take any continuous function. Now take a continuous function that maps to 0, 1 discrete, right? So its image must be an interval because of this. But the only interval contained in the discrete set is either the degenerate interval that's equal to the point 0 by itself, or the degenerate interval that contains 1. So we're done. We know that these guys are equivalent. We don't really need the equivalence, right? We just need to go one further step. But it's actually convenient not to prove that 4 implies 1, but to prove that 3 implies 1. So if you like, we prove that this implies this, that implies this, that implies this, and also that these guys are equivalent. Okay, so let's prove that 3 implies 1 because it's a little bit more convenient than proving that 4 implies 1. And I need to raise more. And now it's really, in some sense, it's the easiest step. Because and we're going to do contrapositive form. We're going to say, suppose x tau is disconnected. that means that it exists L and R, just like this, right? So they're both non-empty. R is L complement, open and close, the two of them. Now I'm going to define an eta that's continuous and not constant on the basis of that. So I just say that eta maps x to 0, 1, and it takes a point little x here to 0 if x belongs to L, and 1 if x belongs to R. Is this well defined? Well, what I need to do is to say that for each little x, there is a uniquely defined value of eta. So each x is either in L or in the complement of L. So this is well defined, and I mean they're mutually exclusive possibilities, right? Either x is in L or in the complement, so you know how to compute eta. Eta is well defined. Is eta continuous? So for that, we need to check that the pre-image of any, say, closed set here is a closed set here. Now, if you look at the pre-images, that's are ridiculous, right? So all pre-images, okay, they're either empty, right? If you take the empty set here, you get an empty pre-image. If you get everything, you get everything. If you look at the pre-image of just 0, that's L. If you look at the pre-image of just 1, that's R. So all pre-images that we talked about, they're closed sets, right? They're either everything, nothing, L, or R. And since L and R are both closed, then all of these guys are closed. So therefore, this function is continuous. And by assumption, it's not constant because we're saying that L and R are both non-empty. So there are points that are mapped to 0, there are points that are mapped to 1. Therefore, if the space is disconnected, there is a continuous function from x to discrete 0, 1 that's not constant. And actually, I mean, so we're done. And actually, it would be very easy to reverse this, to say, if you have a continuous function taking value 0, 1 that's not constant, you can get the sets just by looking at pre-images as 0, 1. So yeah, we're done, right? So we've proved this theorem. By, again, basically we're showing that, okay, if you have a set with empty boundary that's non-trivial, then you can split x in two parts that are both open and closed. If you have a continuous function that's non-constant, that's the same thing as this, if you like, or this. And the existence of mappings from x to 0, 1 discrete, they're continuous and non-constant, implies that some f has an image that's not an interval and vice versa. So we basically proved everything in sort of, instead of giving a characterization of connected spaces, we gave a characterization of disconnected spaces, if you like. Okay. So now I want to finish this video with just a couple of examples, or just a couple of things. One of them is, well, maybe three things. One of them is that pathwise connectedness implies topological. And what that means is that if you have a topological space where any 2 points can be connected by a continuous curve, then it must be topologically connected. How do you prove that? Well, it turns out that number 3 here is a convenient one, right? So suppose I have a function x, a function eta from x to 0, 1, discrete, which is continuous. And I want to prove that it's constant. So what I want to do is to prove that for any 2 points in x, eta of A is equal to eta of B. How do I do that? Well, by assumption, I know that x is pathwise connected. Therefore, there's a curve connecting the 2 points. So there's a gamma from 0, 1 to x continuous with gamma of 0 equal to A, gamma of 1 equal to B. Now I can compose these two things and notice that eta composes the gamma is a function from 0, 1 interval to 0, 1 discrete continuous. And what do I get from this? Well, I have a continuous function from an interval to a discrete set. The only way this can happen is if the function is constant, right? Because if the function, this composition takes the value 0 and 1, both values over here, then by the intermediate value theorem, it has to take all values between 0 and 1. But this is excluded, right? The image of the function contains at most 2 points. And then what I'm saying is that the image of this continuous function cannot contain only 1 point. But what does that mean? It means that eta composed with gamma of 0 must be eta composed with gamma of 1. But this is precisely saying that eta of A is equal to eta of B. So what we've shown is that if you have a continuous function from a pathwise connected space to discrete 0, 1, it must be that any 2 points have the same value of this function. Therefore, X is connected, topologically connected. Okay, so that says that pathwise implies topological. The converse does not need to hold, and I'm gonna give you an example. It's the last thing we're gonna do. I'm gonna give you a classical example of a set that's topologically connected but not pathwise connected. Over the real line, and in a few other cases, however, the two concepts agree. So over the real line, intervals are precisely the connected sets, and the proof of that is trivial, or almost trivial, right? So we know from a previous video that that intervals are pathwise connected. So all intervals are connected as well. What if a set is not an interval? So if a set is not an interval, I have the real line, I have my set, and it contains points x, x double prime, which are both in my set, and an x prime that's not. And then I can do what I did in the proof of 3 equivalent to 4. I can say there's a function, eta, that takes a value 0, 1. It takes a value 0 to the right of this guy. It takes a value 1 to the left of this guy. Right? And the zeta, as you can see, is a continuous function because I'm skipping this guy. It's a continuous function from S to 0, 1, which is now constant because it's equal to 0 here and equal to 1 here. Therefore, if a set of the real line is not an interval, I can find a continuous function from it to 0, 1 that's not constant. Okay, so over the real line, a set is an interval if and only if it's pathwise connected, if and only if it's connected. As I said, that's not always true. There are a few other games you can play too. Remember we had an exercise in the previous video where I asked you to show that if you have two pathwise connected sets and they have non-empty intersection, then the union is pathwise connected, right? So the same thing holds for topological connectedness, but that's an exercise. And again, it's sort of useful to use this characterization. Finally, there's a little lemma that I want to prove that because we're going to use it later, which is this. So assume that you have a connected subset of X, meaning it's connected with the relative topology. And you have a set that it contains C, but is contained in the closure of C. Then this G is also connected, topologically connected. And I'm going to sketch the proof of this. It's also a nice exercise, but it's a bit harder than the other one, so I'm going to give you an idea of how to do it. Right, okay. So here it is. So the only thing, by the way, that makes this complicated is that we have to use the relative topology, okay? And so I'm going to do this. So I'm going to take C. I'm going to pretend that my whole space is X, that is C bar, right? And then we have to think a little bit of what happens if C bar is not the whole of X. But it's just really look at the relative topology C bar. And now I have C, right? C is almost the same thing. So C is sort of like the interior of C bar. And I have D. So D, maybe C bar does not include the boundary, but D includes some points on the boundary, but not others. So maybe this is not in D. This is not in D, but all the other points are. And we have eta from D to 0, 1 discrete. What do I need to show? I need to show that this zeta, which is I assume is continuous, is constant on D. Right? So how do I do that? I'm going to take points. First of all, I know that eta is constant on C. Right? If I restrict eta to C, it's continuous. And because C is connected, it must map the whole of C to a single point. So let's say that if I take a little C here, that it's mapped to 0. Eta restricted to C is equal to 0. Now take a point in D, right? So take a point here. It's like a boundary point. Take a D belonging to the set D. Well, little d belongs to the closure of C, meaning that because of results we have seen, that any open set containing D must intersect C. Now, assume that D belongs to eta minus 1 of 1. Right? Look, this is an open set. And why is that? It's simply because the discrete set 1 is an open subset of this guy. Well, its complement is just a set with a single element 0, which you know is closed. So this is an open set. So if D belongs to eta minus 1, it's it's a relatively open set of D. And then, okay, here's the part where you have to argue on your own. If you have questions, you can ask me. This subset here is relatively open in D. And therefore, you can argue that this set intersects C. Now, wait a minute. Isn't that obvious? Well, almost, right? I said that D is in the closure of C. Therefore, any open set containing D intersects C. But when I said open set, I meant an open set in the whole space. And now I'm saying this is an open subset in the relative topology of D. So how do you get around that? Well, we know what open sets in the relative topology of D are. So in any case, this is an open set that's going to intersect C. And then we have a contradiction, right? Because we just said that all points in C are mapped to 0. So C has no points in the set. So this cannot be. So basically what I'm saying is that if the function eta is continuous and constant and equal to 0 over C, it must be equal to 0 at any point at the boundary of C, any point that's in the closure of C. And what makes it slightly complicated is that we're dealing relative topology. If we're doing metric spaces, what we do is say, okay, if the function is constant equal to 0 inside C, then this is preserved by taking limits, so it's also equal to 0 at any point of the closure. Or kind of like that. Okay, but that's going to be useful for us to know that if you take any subset between C and the closure of C, it's connected whenever C is connected. And with this, I finish this video. Thank